on teacher last year, like advanced, we had questions on even on Gallup also. So I'm not sure about the teacher whether he will show interest or not. So better have an idea. No, what is basically galvanometer? Already we had some we did problems. Without studying this open, we completed our numericals part. So now let's go for the working of galvanometer. Construction and working of galvanometer. So construction and working of galvanometer. So what is a galvanometer? It contains. So basically how the device will be. You just type in in Google Images, no, type it, you can see several types of galvanometer. So this 10 milliampere something we took usually in examples, no, plus minus. These are the knobs which I'll be using for connections. So inside this, and there's a pointer and there's a scale, this one, and these are the leads, positive and negative knob, where if the current which I want to measure, I can go for it. Two types of galvanometer, where the zero will be in the midpoint of the scale and the zero will be on the left hand side. So the zero, if it is there in the midpoint of scale, that will be widely used to get the direction of current. If the zero is there on one side, that can be used to convert the galvanometer into ammeter and voltmeter. Suppose a potentiometer, meter bridge, or even post office box. What type of galvanometer I'll prefer? I prefer galvanometer where zero will be the midpoint of the scale. Or ammeter, voltmeters, all measuring instruments. I'll prefer the galvanometer, the zero in the galvanometer scale should be on the left hand side. So it all depends upon the application where the zero will come. So they may test you with small basics here. In fact, in advanced exam, when we ask such questions, students they found a little bit difficult. So I'll just indicate. See, it's not your problem since you are not entering into the lab, no? So things will be a little bit very random for you. 5, 10, minus 10, minus 5, 5, 10. Milliampere. So this particular galvanometer is used in meter bridge, Wheatstone network, post office box. Next, galvanometers. Zero, 5, 10, 15, 20 milliamperes. So look at the pointer. Where is the zero? The zero of galvanometer is there on the one side. So this galvanometer sort of we use exclusively for. So zero I'll indicate by some color. Yeah. You have to just make here. So these such are used for ammeters, voltmeter. In simplest, in nutshell, where direction has to be noticed, the zero should be the midpoint of scale. Where only magnitude of current is to be measured exclusively, I'll go for zero on the one end of the scale. Fine. Okay, let's come for this one. So here now we are discussing about the galvanometer. Which kind? For we can the same mechanism. Little bit some changes will come. The same mechanism will be there. So let me focus. We are discussing a problem of this kind, where the zero is the midpoint of scale. It will be. So no much basic difference will come. Slight changes will be there. So that's not part of a syllabus. Let's not bother. So we are just learning a galvanometer. Is it okay? No. So here, as I pass a current, as I pass a current, as I pass a current, the pointer will deflect. And what should be the deflection of pointer? The deflection of pointer should be proportional to magnitude of current, no? So all my design should be such that the deflection in the pointer should be proportional to the current. How to make that? How to deflect the pointer? So let's go for dipole moment, current carrying loop kept in manifold. It will rotate, no? If I can connect a pointer to that rotating loop, so if I'm able to rotate the pointer, yes, as the current flows, the pointer is going to rotate. So that's what the mechanism. So what I do is, this is a coil. You can see the labeling. This is a coil of N turns. And where it is wound? It is wound on the core, iron core. This is a cylinder. I'll shade all one by one. Try to, so this is a cylinder. So what is this? Iron core cylinder. So first what I do, I'll take iron cylinder. I'll take iron cylinder. And I'm going to wound a coil on that one. So what should be the, so it will be the iron cylinder. Let it be this one. Now I'm going to wound a coil. So how I am going to wound like this. Some n number of turns were there. This is iron core. And what is this red color? Red color is a wire loop, current carrying loop, n number of turns. Just go back to the dipole moment. Within 5 minutes, this will get over. Nothing big. Now, sir, like what is this made up of? Loop. What is made up of? Copper, no? Copper winding. So there's nothing but what? Copper wire. So short circuit will happen. No? So for that, what I do is I'll take iron cylinder. On that, I'll give insulating coating. On that, I'll give insulating coating. Then what when I'll take copper wire, I'll wound it. Again, the turns will be wound very close because the flux should not, the field should not escape between the gap between the turns. So again, what I do, I'll give with a brush, I'll apply insulating layer. Then again, I'll wound one turn, first turn. Then with brush insulating layer. Then second turn, third turn, like that. The in a small gap, no, in a width of 1 centimeter, I can go for 500, 800 turns. It all depends thickness of copper wire. Got this? So we are not bothered thickness here. We are bothered about number of turns. So therefore, I'll go for thin copper wire. So they may test you with small basics like this here. Iron cylinder. So what is this galvanometer? You can hold in your hand, not something big. You can hold in your hand. So definitely what should be the iron core? Should be small. So I need more number of turns. Around 200, 500 turns will be wound. A thin copper wire is taken. So iron copper short circuit will happen practically. So first iron cylinder on that insulating coating, then I'm going to wound a wire. When you play kite, how you wound thread on that wheel, no, the charka, the similar way, or you take some cotton thread, just wound thread on your finger, the similar way what we are going to do here. So why number of turns? Because the dipole moment will increase by n times. Okay, fine. This now I'm going to keep this in magnetic field. If I keep this in magnetic field, and I'm going to keep this in magnetic field here. And now come for the torque due to dipole moment idea. If there is a current carrying loop is there, n turns are there, and this is I, this is M bar, and this is B bar. Tell me how the loop will rotate. The loop will rotate like this. If I pass a current I, then what is the equation you are going to write? Torque equal to M bar cross B bar. What is M? N I E. What is N? N is number of turns. I'm not showing that number of turns here. Into this is B sine theta. This will be sine theta, because as the loop rotates, what is the angle made by the, so this is the angle, no? Look at this angle, no? So sine theta will come into picture. So torque acting on this constant or variable will be variable, no? This is. So now what is the mechanism I should bring it? Okay, when a current flows, the loop will rotate, and because of torque acting, it will accelerate. Because of torque, it will accelerate, and it will have angular velocity. Then if I make current zero, what should happen? The pointer should come back to, return back, no? This was the mechanism, am I right? If you pass a current, the pointer will deflect. So here open this pointer, I'm going to connect to the loop. So somewhere at the midpoint, the pointer will be connected. So as the loop rotates, what will happen to corresponding to the pointer? The pointer is also going to rotate, no? Trying to see the mechanism. So what is that green color? This is a pointer. As the loop rotates, so the pointer will also rotate. So now shall I say somehow I brought it some deflection of pointer? Getting now? Now, so what is the problem here? Look at the torque acting, NIAB. So we are getting this much. So this torque is what? Due to dipole moment. Now if I make current zero, practically what will happen? If I make current zero, M bar will become zero. Then it should come back, the pointer should come back to zero, no? To show that no current. And go for practically. Now you know enough ideas of this. The moment I pass current, torque due to dipole moment will act, then torque due to that angular acceleration, then due to that angular velocity will act, and due to angular velocity, so when the loop will be rotating, no? And the torque acting will keep on decrease, will become zero. So what type of motion the loop is going to describe? Variable angular accelerated motion. So suddenly you make current zero. So will pointer will stop there only. No, because of angular velocity, what will happen? It will rotate and it will go and touch the maximum value also. Then where is the question of measuring it? So what sort of mechanism we needed? We have to measure, no? Able to analyze. So we need a mechanism where it should measure. Means if I pass a current of 1 ampere, 1 milliampere, the pointer should be at 1 milliampere. It should not move continuously. If I pass 5 milliampere, the pointer should be at 5 milliampere. If I pass 6 milliampere, pointer should be 6 milliampere. Then who should stop the pointer? Here, I think nobody is there to the moment you pass current, what happened to loop? Loop will continuously start rotating. Though you make current zero open due to inertia of motion, due to acquired angular velocity, will continue to rotate. No, so tell me what I should do here. I should really bring some other torque which will balance this. How much of torque is due to torque as the loop rotates. Equal and opposite torque should be set up and immediately should be brought to rest. So a restoring torque should be acted. So you can see restoring spring. Restoring spring is brought here. So that restoring spring is what we are showing here in the form of like this. Or here you see this diagram. So here I'll call this as restoring spring. Now, what should be the mechanism? As I pass the current, the loop will rotate. Then there should be equal and opposite torque set up by this restoring spring. So how do spring force can produce torque? So here like a wire. So can you go back to torsional oscillations? There what happened? The wire got twisted, no? And in that what happened? There will be like a couple per restoring torque is set up, torsional oscillations. Similarly, same thing, this particular wire will get twisted. So the torque set up in the wire, what happened, will be equal and opposite to torque due to dipole moment. So when you pass 1 milliampere, torque due to dipole moment, due to that it will rotate. Then proportionally what happened, torque due to elastic forces will be acting opposite to that. And because of that what happened, the pointer will gradually and will come to a rest. Then 1 milliampere you have sent it, the pointer will come and deflect it, will stop at 1 milliampere. So what is basically our mechanism now? The mechanism of design should be on a loop, on a loop, this M bar, this is a B bar. So there should be some sort of, I'll show spring like this. Now this will be much easier. This is spring, or it's a wire only, like a torsional wire. It is. So as it rotates, as the loop rotates now, what will happen to the wire? Wire will get twisted. Don't take it similar to like a spring force, because that elastic forces only. Therefore, I'm just showing like a spring here. So this is the I bar. So M bar like this, and this is B bar. So M bar cross B bar. So torque due to magnetic field will be like this. Torque due to spring, or the wire will get twisted. No, will get like this. This is due to wire. Understanding the mechanism. They may test you with some questions like this. Of course, mains, no, they may ask you small question, but anyway, you should have a basic idea. This is the thing. Earlier M bar angle was 90 degree. Now we brought it this one. So what should be the torque due to dipole moment now? Due to magnetic field, M N I A area of cross section, B sine theta. Look at now here, theta is there, no? Theta is the angle between them. I should make this theta 90 degree for all the portion. Means though it will rotate, but M bar should be always directed to B bar. How it is possible? I should eliminate this theta. Should be eliminated. How to eliminate means theta must be made 90 degrees. So M bar must be always perpendicular to B bar. For that purpose, what we'll go for radial field. Look at now for all the positions. So here how M bar will be directed. These arrows are the direction of the magnetic field. So who will produce the magnetic field? These magnets. This is the magnet. Instead of bar magnet, the bar magnet only what it's say they are curved, and the uniform air gap is maintained. Uniform air gap is maintained between the core and the bar magnet. Okay, look at the field how it is radial. No? In any position, how M bar and B bar will be directed in any position. So M bar direction, I'm showing it here. As the loop rotates for all the positions, how M bar will be. M bar should be perpendicular B bar, because how B bar, no, B bar is tangential to the loop, no. Instead this, if I go for just bar magnet, let's do one thing. We do have two types of this one. This is core. Next we have the bar magnet only. What pen? Its edges sort of are made curved so that the air gap will be uniform. So you have this one. So what is this? This is the core. Huh? This is the winding. This is a north pole, south pole. This is a north pole, south pole. Let's come for the direction of B bar. B bar, I'm taking this. The B bar will be produced by like this. Will I agree? The direction of B bar. So what is the angle between B bar and M bar for different positions of the thing? And let this be the current I. Now what about B bar? How B bar will be directed here? This will be the direction of this one. So for all the positions, is it B bar perpendicular to M bar perpendicular to B bar? So this is the direction of M bar. No. For all the positions, I'm sure that M bar will be perpendicular to B bar. Will I agree? Now in this position, M bar is perpendicular to B bar. As this core rotates, when a current I flows due to flow of current I, so what happens? A dipole moment is set up and M bar rotates. So even for next position also, you slightly rotate this. So we'll do one thing. So here A, B. Okay, now tell me like how AB is there. AB is along the direction of B bar only. No, the same thing. Now the position of A is here. It has rotated, and the coil number of turns. The coil turns are like this. This is the direction of current I. And now you see that how M bar and B bar will be now. It has rotated. It got deflected. So what is the direction of M bar? M bar is like this. Now because of this radial field or uniform air gap, the air gap. This is what the air gap. So look at this air gap now. We'll call this as the air gap. This is the core. This is the magnet. This is the air gap. This is the magnet. Okay, to make the scale linear, clear this one. So now for all these positions, what happened? The M bar and B bar will be 90 degree. So what happened? The theta eliminated. The reason for that, because the scale should be linear. The scale should be linear. So to make the scale linear, what happened? We are eliminating that particular theta. So how to make that scale linear? By going for a curved shaped magnets here. The air gap between the magnet and the core should be uniform. So therefore the sine theta will become sine 90 will be 1. There's the reason. Next again, why do I go for what should be the magnet? Magnet should be powerful. They should be the powerful magnets, or they should able to provide more field. There's the advantage. Next, why we are going for iron core? Because the net B bar will be more. Because what is the mu r relative permeability for iron? It will be almost around say like a 10,000 something, or say 2 lakh something. The field strength without iron, the field strength will be say B. Then with iron core, what happens? It will increase by almost 2 lakhs. So therefore, the field strength I'm going to increase by iron core. There's the advantage of using iron core. A ferrite cylinder, it is called as. So this should be purely an iron core. Got this now? So first, how do we eliminate sine theta? To make scale linear. Why we should eliminate theta? To make scale linear. Okay, let's come for the overall. This is about the thing. So let's write some mathematical equations. So how do that current will be measured? We'll write some set of equations. Okay, let's go for the writing the equation. So what is the torque due to dipole moment? Torque due to dipole moment Ni, area of cross section A, B. What is B? B produced by the bar magnets into sine theta. This is the torque due to dipole moment. What is N? N number of turns, I is the current, A the area of cross section, B is what? B bar produced by magnet. Theta is what? I'm going to make angle between M bar and B bar. Then according to this setup, here sine theta will be non-zero. What about sine theta for these diagrams? Sine theta, theta will be 90 degrees, no? Theta will be 90 degrees. So sine theta how much? Equal to 1. So because of radial magnetic field, sine theta will be equal to 1. So then this will become NIAB sine 90. Why sine 90? Radial magnetic field. Write it here. Or M bar perpendicular to B bar. Okay, these are both this one. And now, this is the torque set up by magnetic field. There's a deflecting torque, no? Shall I call? Deflecting torque. Oh, deflecting torque due to current I. Now, if I, who should oppose this? That's particular spring. Can you remember, no? So torque due to, now what happened? A restoring torque should be brought here. Why restoring torque? I think you know enough of, we have discussed so many problems. There's only idea this one. If this torque due to wire were not there, now if you pass a current, torque will act. And due to torque or angular acceleration, due to acceleration, angular velocity. So what happened to pointer? Pointer will continuously will rotate, no? The loop will continuously rotate, pointer will continuously deflect. But what is our mechanism? It should stop for a while, no? It should stop at certain point because it has to show how much of current flowing. The pointer, the loop should stop rotating. So for that, I am bringing now restoring torque. This is a deflecting torque. This is a restoring torque here. So when the pointer, when the loop starts rotating, when the deflecting torque, I'll bring it here. When restoring torque is balanced by restoring torque from where I'll bring couple per unit twist. So this is symbol C, or some books they took beta, anything that one. I'll take beta because C again you may get confused, any symbol beta, couple per unit twist into, call this is some angle. Couple is torque, no? Torque per unit twist into that angle. This should be equal to what? This one. So beta phi, this will be NIAB. So what is the formula now? Current equal to, you see now, beta by NAB. This is phi. What is phi? Phi is the deflection. Phi is the deflection of loop or pointer. From where this restoring torque produced by the spring. What is beta? I'll put all this one. This is like a torque per couple per unit twist, or torque per unit angle. Torque per unit angle into angle will be the torque only, no? From where this should be produced by the spring. So as you pass current, what will happen? The loop will rotate. As it rotates, what will happen to spring? Spring will set up a retarding torque or a restoring torque. And finally, what will happen? Where the pointer will come and stop at certain angle. And look at that particular current. Current is now proportional to angle. Now this should be the angle now, to which the pointer should deflect. So what I made now, beta, I think, okay, there are symbols are there, beta, capital B. I'll make it C only, huh? Because again, B and beta, capital C. Okay, we have this one. So shall I say that I is made proportional, what is C constant, N number of turns constant, A constant, B constant. So how I is proportional to angle. So it's a linear scale. No, no. If you don't bring radial magnetic field, tell me what will happen here. We'll end up with sine theta, no? Then how our expression will be? Our expression will be sine phi NAB sine theta will come. So will it be scale linear? I will be proportional to, so sine phi, you write it. Will it be proportional? Anybody? Will it be linear? Sorry. This will become non-linear scale, no? This will become a linear. So you send current 1 milliampere. It will have a deflection of say like a 1 degree, 2 milliampere, 2 degrees, 3 milliampere, 3 degrees. But here will not be like that. The scale will be non-linear. So therefore, how to eliminate that sine phi? Angle between M bar and B bar by bringing radial field here. So now this will be a linear scale. So got the mechanism. So now how that all happens here is what you can see from the diagram. When you pass a current, the coil here, a torque is set up and it starts rotating. As it starts rotating, this wire will get twisted up. So it will set up a restoring torque. And the pointer weapon will come and stop at one point. So at this particular point, as long as current I is flowing, torque due to dipole moment will be acting on the loop. And the wire got twisted and the pointer rotated. So the restoring torque is balanced by the deflecting torque. And the pointer will be there as it is, there only. Now I'll increase current. The torque due to dipole moment will increase. The pointer will come here. So you can see that one. If current is 0, it'll be here. Now I'll increase current. It's 1 milliampere. Then some torque is acting. Torque due to dipole moment is acting. Then as the pointer rotates, as the loop rotates, the pointer will also deflect. And the spring will get twisted. So equivalent opposite torque is set up and gradually the pointer will come to rest here. So net torque is 0, it will be there. As long as current is flowing, the pointer will be here. Now I'll increase current, 3 milliampere. Also like it has become 0, 1, 2, 3 milliampere. Torque due to dipole moment will increase. The wire will get more twisted. So restoring torque is set up. Again, at this particular point, torque due to dipole moment is balanced by torque due to the wire. The restore torque due to spring. So as long as current is flowing, will be there only. Now, if I make current 0, what should happen to the coil? What should happen to the pointer? Should come to 0, no? Can it come? Yes. Who should bring it back? If I make current 0, torque due to dipole moment will become 0, no? Then the spring which was got twisted, there the elastic forces will act and will bring back the pointer to 0. Are you getting the mechanism? So what is the use of that restoring spring? That is the main thing. If you don't have that spring, so you pass a current or continuously it will rotate. But when you pass a current 4 milliampere, when you pass 3 milliampere, it should be here. When you pass 5 milliampere, it should be here. If you make current 0 here, so somebody should bring it back, no? So who will bring it back? The torque set up in the spring, it will bring it back. So is it okay, justified? I'm writing in the diagram restoring spring, or to set up a restoring torque. So initially what happens when you pass a current, what is the spring? Spring is not deformed, undeformed. Then torque due to dipole moment will act. As it starts rotating, the torque in the spring will increase, continuously increase. Then what will happen? The angular acceleration continuously decreases. And finally what happens? It will come to it. This all happens in a fraction of time. So there's a mechanism. So as you pass current, the pointer will deflect it. So how the current and deflection should be proportional, no? To make it linear, a linear magnetic field, a radial magnetic field is brought here. Got the idea, no? So there's a method is what we are following. A concave mirror is used to show that particular So like a parallax error. If the pointer is here, no. So definitely what happened? To avoid that parallax error, the concave mirror is used. That one. So if you see from either side, no. So to avoid parallax error, what happened? The concave mirror is used here. Okay, got this. So overall, about the working of this one. So finally, what happened? We are here. Okay, this is the thing we'll try to avoid, no? The non-linear scale. So this is not suggestible. How to make scale linear? How to make scale linear? By providing constant air gap between the magnet and the iron core. So I proportional to deflection. So this is the angle through which the pointer will get deflected. So what is that phi? Again, you'll get confused. So I think I wrote somewhere, no? Deflection of loop or pointer. But still what an angle between M bar and B bar will be 90 degrees only. Okay, finally, so we are in a now better position to this one. So now I want this particular galvanometer to be more sensitive. What do you mean by sensitive? Sensitivity of galvanometer will define it. Current sensitivity. Current sensitivity, I'll write it SI. There's no specific symbol. Let me write SI, that one. So it is defined as deflection per unit current. Deflection produced per unit current. Deflection produced in galvanometer per unit current. So this should be what? The phi by I. So what is phi by I should be equal to NAB by C. Look at, no. So what do you mean by current sensitivity? Even if you send a small current, the pointer should deflect, no? Then only called as sensitive. Means microampere I'll send, 10 microampere. I should be able to measure the 10 microampere. So and say like a, what is the least, suppose say 1 division, 0 to 10 milliampere, and there are 10 divisions are there. Tell me like a, what is the least current you can measure? What is the maximum current? 10 milliampere. There are 10 divisions are there. Then what is the least current you can measure? Minimum current. Minimum current is 0.1 milliampere. Then I have another galvanometer, 10 microampere, and there are 10 divisions are there. What is the minimum current I can measure? 0.1 microampere. Oh, sorry, 1 microampere. This is. Tell me like a, which is more sensitive? This one, no? The left hand side. Even a small current of 1 microampere I'm able to measure. So shall I say this is more sensitive? Select I sensitive compared to, and this is low sensitive. If you're able to measure, it means even if you pass a small current and if you're able to notice the deflection, that's said to be sensitive. So how to increase that sensitivity is telling here. So how to increase current by increasing number of turns. If you increase number of turns, the size will increase if you increase number of turns. So number of turns is of course to certain limit what when I can increase here. Then what is another mechanism? By increasing area. If you increase area, the size of galvanometer increase. So this is not suggestible, no. And if you increase number of turns, what happens? The resistance of galvanometer, because more number of turns, more resistance will be added. The resistance of galvanometer will increase. So therefore, there's some limit for increasing number of turns. And if I increase area of cross section of loop or the cylinder, nothing but. This particular, I'm going to wind this one, no, on the cylinder. So what is the area of now? Area is not area of cross section of pi r square. You should take this rectangular area, this one. So as you increase the area, what will happen? Current sensitivity will increase, but proportional when the size of galvanometer will increase, no? Then next B, I should increase the magnetic field strength. Who will produce that magnetic field strength? The bar magnets. So I should go for powerful bar magnet. Another method of increasing field strength here, linking the loop by going for iron core. So why we'll go for iron core? Because the field strength produced by bar magnet will be multiplied by several lakh times. So therefore current sensitivity will increase. Or next what I should do? Couple per unit twist should be small, no? Couple per unit twist should be small. So if the couple per unit twist is small, then so I'll prefer a phosphorus wire. What is that spring made up of? Spring is made up of phosphorus. So this particular spring, we prefer it to be made up of material. Now why phosphorus bronze is used here is the restoring couple or the couple per unit twist for phosphorus bronze is very small. Next again, it is having more tensile strength, great, very high. What do you mean by tensile strength? Means even if a large torque is set up, then it will not break up. Very high tensile strength means like as you uh, as you start using this galvanometer, your pass current will decrease, again make zero, again increase, again decrease, no, like that happen. The wire will be continuously will be twisted, untwisted, twisted, untwisted. So the tensile strength of that should be more, or the lifespan of that should be more, and it should be high tensile strength. So the wire what happen will not break up, because if the wire gets break up now, I should open the total galvanometer. Better to you have to put in dustbin. So the spring becomes very, very important. So with the time what happens, the strength should not decrease here. So therefore, high tensile strength. So that's why the phosphorus bronze is. What is the advantage of that? Couple per unit twist is very small and a very high tensile strength. Means breaking up of spring, what when spring get cut is highly impossible. That's why the phosphorus bronze for that will add phosphorus and may make it old. So it's a very important alloy it is, which is widely used in the applications. Chemistry, metallurgy, there's the advantage of that one. Why not iron? Why not copper spring made up of material? These advantages are there. The breaking strength should be more. It should not get easily cut. So how to increase current sensitivity? So I'll prefer C to be I. So C should be low. Then A, what happen? I'll should be as small as possible. No? Then the galvanometer will be more, will occupy less space. The size should be not more. So therefore, increasing A is ruled out. I'll increase number of turns. Instead of one turn, I'll go for 100, 200 turns. So why in the galvanometer on cylinder only one turn? Why 1,000 turns are there? Why not only one turn? To increase current sensitivity. Are you getting? Then how the B bar? Strong bar magnets and iron core. We'll see that B bar will be more. So this is about the current sensitivity of this one. Similarly, can we go for voltage sensitivity? Because that particular loop what happen coil will have now we'll define one more quantity called as voltage sensitivity. So what is voltage sensitivity? Deflection, this will be SV, deflection per unit voltage. What is the deflection? Now, there's a deflection of the point of the loop. And what is voltage? Voltage applied across the loop or across the galvanometer, and I into R. What is phi by I? NAB C into R. Now you see that one has an increased number of turns. what will happen to voltage will increase. Proportionally, the resistance will increase, no? As N increases, R will also increase, because what is resistance? Resistance proportional to length of the wire. More number of turns, more resistance will be added to the loop. So now come for this one. If I increase current sensitivity, proportionally voltage sensitivity will increase. So this is deflection. Per unit voltage. If I increase the number of turns, proportional resistance will increase, no? So therefore, what will happen to voltage sensitivity? May not change or may change, no? It all depends upon this ratio of N by R. So if I increase current sensitivity, voltage sensitivity also increase. Will you justify this answer? Need not, no? So therefore, if I increase current sensitivity, voltage sensitivity changes or remains constant. It all depends that one. So here you can see that as the increased number of turns, current sensitivity will increase. But if increase number of turns, so what will happen to voltage sensitivity? May or may not change, because the resistance also will proportionally increase. If the ratio of N by R remains constant, the voltage sensitivity remains constant, while current sensitivity increases. So therefore, if current sensitivity increases, if SI increases, SV necessarily need not to increase. Will I agree this statement? Because R has come into the denominator. So there's a relationship between, when you're designing ammeter, you look at current sensitivity. When you're designing voltmeter, you look at the voltage sensitivity. That's the basic idea. Okay, this is about the galvanometer. Now, what we have is like, when you start using this galvanometer, not I didn't write, necessarily need not to increase. Okay, need not, yeah, I'll underline. Thank you. Necessarily need not to increase. This statement is very important. Now, okay, finally what happened, we are able to measure that. So what is the maximum current I can measure? Shall I say it depends on the current sensitivity and all these particular parameters. So like that we'll define the maximum current which a galvanometer can measure. That is what IG know. We say 10 milliampere, 20 milliampere. That depends upon the current sensitivity also. Now this total galvanometer will offer some resistance, no, to the flow of current. So I should find out the galvanometer resistance. How to find out? So what is the method? So where all the resistance will come? Resistance of this coil, resistance of this coil, resistance of the coil, and also what happen? A current should flow through this spring also, because overall setup will be like this. The current, it will pass through this particular thing. So then this connecting leads inside here from coil to this particular thing. So what is the resistance of galvanometer? The resistance of the coil and connections made by the coil to the leads. This one here inside, I'm not showing that. And even this knob also will offer that everything will become a galvanometer resistance. How to find out that? Very difficult quantity. So definitely I should bring an experiment to measure the galvanometer resistance. So for that, current deflection by off deflection method, measuring the resistance of galvanometer by off deflection method here. So let me go for the experiment. Okay, this is a circuit. There's again one small formula I'll generate. What is the galvanometer resistance? Resistance offered by galvanometer resistance. Galvanometer resistance by off